Hey, this is Dr. Lyle Raccoon, and I'm going to be talking about an overview of Bayesian statistics. We're going to keep this kind of high level for this introductory part of the course. Bayesian statistics is kind of neat because it's pretty intuitive. We use it quite a bit in our daily lives. So, right now it's raining where I am, and the weather forecaster said, there's like a 20% chance of rain, and you might be thinking, okay, so 20% chance of rain. Do I bring my umbrella or do I just go out and not bring an umbrella? And you're going to make that decision based mostly on prior knowledge, your history, your experience with, whether or not it's going to rain when the forecast says it's 20% chance. And when you do that, when you use your prior experience to kind of inform your decision making, you're being a Bayesian. That's basically the intuition behind Bayesian statistics. We use some of the prior information that we know, some of the information based on our experience. Maybe we use information from other studies that have been published, and we use that information to, combine with what's happening in the real world right now to come at some kind of decision. So, what is the probability that it's actually going to rain outside? It's 20% chance is what the weather forecaster is saying. Whether or not it's actually raining where you are or where I am is dependent upon all kinds of things, and the model's making its best guess. Now, if they were to say it's an 80% chance of rain, am I going to bring my umbrella? I probably am. But, 20% chance, I may or may not, because what that means is that the probability in some specific point that the weather forecast is talking about, it's only a 20% chance that you'll actually get hit with rain. So that's kind of the intuitive nature of Bayesian statistics. And, I want to go through and show you some more of how this actually works. So what is the objective of a Bayesian statistical analysis? Well, really, it's to find the probability of something given some data that we have, right? So if we're talking about toxicology, that's the probability that a drug or a chemical exposure is going to result in some kind of toxicity, or maybe that doesn't result in some kind of toxicity, right? So we want to know, is this candidate drug compound going to cause some kind of bad thing in people who might take the drug? What's the probability of that? That's kind of the toxicology side of things. If you're more on the pharmacology side of things, you might be wondering if the drug exposure is going to result in some kind of therapeutic effect, right? So that's really what the objective of Bayesian statistical analysis really is it's trying to get this probability. It's much like the probability in the weather forecast example I gave, right? That's ultimately what we're trying to get at, is some kind of probability about something. And maybe it is the probability of cancer when you are exposed to a particular concentration of a drug or chemical. Maybe it is the probability that you have, you know, um, the tumor shrinking when you're exposed to a certain level of this drug. It could also be, what is the probability that the um, ALT level, if you're looking at liver toxicity, that the alanine aminotransferase level is between a couple different numbers. What's the probability that the ALT is elevated compared to control? These are all things ultimately that we might be wondering about, and Bayesian statistics helps answer that question. So why do we even bother with statistical analyses in the first place? And this is a pretty good place to start. I want to make sure we're all on the same page here. Generally speaking, it all boils down to inference, right? That's what we actually care about. We're trying to infer something, because typically what's happening is uh, we need to measure something, and then we want to infer what's going to happen in the larger population. Because we can't expose everyone in the population, we have to sample, right? So we're going to grab some individuals. It could be people. Maybe we are going to do this as an animal study. Maybe we're going to do this in vitro. Ultimately, we can't test everything. We can't test everyone. We can't test all the cells in the universe. We can't test all the mice in the universe. We can't test all the C57 black 6 mice. So we ultimately have to figure out how we're going to sample from this population. And the hope is that by sampling, what's going to happen is we're going to have this sample that's going to be representative of the population. So in classical or frequentist statistics, and I'm making a very large generality here, but it suffices for our purposes. Um, and here, think about ANOVAs and t-tests, right? The things that we normally would do, we would normally publish in a scientific paper. We're assuming that the sample really does recapitulate or reproduce the population really, 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 really well. Now, whether or not that's true is up for debate, and typically if you have very small sample sizes, this will not be true. So, just throwing that out there. In Bayesian statistics, we do assume that our sample recapitulates the population to some degree because otherwise inference just doesn't work. But we're going to temper the data that we get from the study that we're doing today with information, historical information, or if we don't have historical information, we might use some other subjective measures to help inform us about the uncertainty in our sampling. So what I'm trying to say here is we understand that information that came before us may be helpful, especially if it was a well-done study, and that we're going to combine that information with the information we're getting from today's study in order to basically create a better understanding of what the population distribution probably actually looks like. So it's very nice from that standpoint that we're using what came before us. We are leveraging the previous investments in science to help us get a better inference on what the population might be. So here's an example I like to give. This is some data for carbon tetrachloride. And you can see here that we've got control, that's the dose 0, and we've got a high dose of 100. I forget what the units are. It doesn't really matter in this case, but you can see control has a much higher alanine aminotransferase level than the high dose of carbon tetrachloride. And, naively, some authors have said that, oh, well, this proves that carbon tetrachloride at this high dose is actually hepatoprotective because it's much lower than in the control. And for those of you who aren't familiar with alanine aminotransferase, or ALT, ALT is a measure of liver injury. So what happens is as the hepatocytes start to lyse, they are releasing this protein, alanine aminotransferase, into the blood, and then we can measure that. And so if you were to get a physical and they take a blood test, ALT is one of the things that they'll be measuring. And it's not uncommon in toxicology to use ALT as a surrogate for liver injury. So if the ALT is elevated, then that would mean that there is likely toxicity. But in this case, the ALT is less than control. It's kind of interesting, isn't it? So perhaps it is in some way hepatoprotective. Is that true? Now, as a liver toxicologist, I'm going to tell you no. And based on my knowledge and experience, I can tell you this is not a real thing that's going on here. What's happening is the normal range for ALT is pretty large, and this ALT for the controls is actually kind of on the middle of the distribution, and this number here for the high dose of carbon tet is really on the low end of, or even still within the middle range of where the control should be for ALT. But if you're a frequentist, you run this through your t-test, guess what happens? It comes out significantly different in your t-test. But a Bayesian would look at this and say, but I know that control spans, such a large range. I just don't believe this. So as, what we would do as a Bayesian is we would use other vehicle data from the same study or other vehicle data that has been published for ALTs. And, if we had a historical database of ALT values, which there are, a lot of companies keep that kind of information, they could actually do a Bayesian analysis and they could come up with probably a distribution that looks like this. So here we're looking at other vehicle data from the same study. And you can see it actually in the controls, it has a pretty wide range. It's going from, 25 out to 50 units. That's a pretty large range. And if you remember, if we go back here, the mean here was around 35. Well, here's 35. It's like smack dab in the middle of the distribution here across a lot of different animals. So we can use this information as Bayesians to build what we call posterior distribution for the vehicle ALT level. And so now we can see this curve here is the original data that we had from that box plot. That's what that curve represents. And then the histogram, these bars here, is the data that we got from the model. The model does a pretty good job of recapitulating the data. And moreover, what we can see is we can get a better idea as to, yes, most of the vehicle ALT is really going to be between, about 25 and about, let's say, close to 43 or 45, right? So it's really within that range that we see it. But certainly lower values are very credible, right? And like I said before, for toxicity, we don't expect the ALT levels to be lower. We expect them to be higher. So what we can do is we can do the same thing again for the high dose. We build out this distribution and, same thing. The model is the bars. And then this curvy thing here is the data that we have. And now we have a posterior distribution for the high dose. We have a posterior distribution for the controls. And then what we do is we just subtract them. Or we can compare them. So here, I'm just overlaying the two distributions, right? So the vehicle is this smaller, flatter curve. The high dose is this curve over here. And we can see that the high dose distribution is completely contained within the vehicle dose distribution. If there was toxicity, we would actually expect the high dose to be on the upper end, past 50. But it's not. It's almost entirely contained within the same range as the vehicle distribution. So looking at this, what we can see is that contrary to what we saw in just looking at the particular study, just looking at the controls for that particular part of the study and looking at the high dose, here, frequentist statistics tell us this is statistically significantly different. But what matters is we need to bring some biology back into this, right? So as a biologist, I say, no, this doesn't matter. This isn't real. And then as a Bayesian, I can look at it and I can see, yeah, really, statistically, this isn't even real. This isn't a thing. So this is kind of the power that we get when we start combining this other information from other similar studies to help us better understand, in this case, just the controls. We're getting a better indication of what the control distribution is. I don't have a lot of historical data for carbon tetrachloride. But I have a lot of other data, including historical data, for the control. And just having that information is enough to improve our interpretation of the study. So what we're seeing is really the conventional approaches, using like t-tests and ANOVAs, they're comparing the mean estimates for the vehicle response versus the treatment response from just the study we are looking at. And it can lead us to some really wrong conclusions. And a lot of this has to do with, I'll be honest with you, a lot of this has to do with the fact that these are small sample sizes. The studies that we're talking about here have an N of 3. And this is the problem. When we deal with small samples, this is the kind of stuff that we have to expect. That's one of the advantages of the Bayesian approach, is that at least for controls, we might be able to get additional data. We might be able to do a better job of modeling what that population distribution looks like. The Bayesian approaches are embracing the whole of the distribution instead of just the means, which means we are also getting that uncertainty. And we're comparing the full distributions to each other. I think I mentioned in passing before, when we're looking at these two distributions, I can actually subtract the vehicle from the treated and come up with what's called a difference distribution. And then there's ways of using highest density intervals and regions of practical equivalence, which we'll cover later in the course, to really get a better idea as to what's actually happening and is this statistically important. But the beauty of the rope concept is that the region of practical equivalence allows us to put bounds that are biologically determined. So now we can combine our biological knowledge of what an appropriate effect size is, something that is biologically meaningful, into the statistical calculation to allow us to then draw better conclusions. So because Bayesians are using a modeling framework, you can also update your model easily as new data comes in. So what's the real advantage of using Bayesian technologies and approaches for pharmacology and toxicology? It's the fact that we have this historical or other data that we can bring in to inform our analysis. And mathematically, what we're doing is really using Bayes' theorem. And this slide goes over it. I'll just go over it really quickly. What we care about is typically the probability of some effect E given some treatment T. And that is explained by this formula right here, where this part here, the probability of treatment given effect, that is what we measured in the study. We also call it the likelihood. This PE, that is the probability of the effect. That's our prior. If we have historical information, it goes here. And then this denominator here is a normalizing constant, or I shouldn't call it constant. It's a normalizing factor that keeps the posterior probability between 0 and 1. And here's a really good example of how this all plays out using something that many of us may be familiar with, and that is a diagnostic test. In this case, I'm going to talk about cancer. So let's assume you went out and you got a diagnostic test for cancer, and the test has a false positive rate of 10%. Let's also assume it has a true positive rate of 95%. The prevalence of this cancer in the population is extremely low. This is a very rare cancer. It's 0.001%. So what's the probability that you have cancer given that you got a positive diagnostic test? Well, we will use Bayes' theorem, and you can see this is how it all fits together, right? So what's the probability that you have cancer given that you got a positive test? And it's equal to this mess right here. And when you start plugging in these numbers, here's the true positive rate. This is the prevalence of the cancer within the population. Again, true positive rate, prevalence plus, and this is 0.10 because this is our false positive rate times, and then this is the probability that you don't have cancer, the prior probability that you don't have cancer. So it's 1 minus 0.00001, right? Do the math, and ultimately the probability that you have cancer given that you have a positive test is 0.009%. So you likely don't have cancer, but most people don't like cancer. So if this is a cancer that's particularly aggressive, if this is a cancer that is really painful, awful, this is a case where you probably should get another test, right? And maybe you get a second opinion. It's not a very common cancer, but that doesn't mean it's not there. So you want to do some additional confirmation beyond just this diagnostic test. And this is very common for screening tests, right? These types of false positive rates and true positive rates are very common for a lot of screening tests. The same could be said for pregnancy tests as well. Now we can also do really, really, really complex models. This is a model here that we used. It's what we call a hierarchical model. We published it in a paper with Claudio Fuentes and Chris Borgert in the Archives of Toxicology recently. And what we're trying to do here is we're trying to calculate this bottom thing, which is mu, which is the global Michaelis-Menten equation for a biological system's pharmacokinetics or toxicokinetics of a chemical. Ultimately, this is our approach to driving a kinetically derived maximal dose. If you're really interested in this, I suggest you read the paper. I'm only showing this to show that we can do some extremely complex modeling within the Bayesian framework. And we can do some really cool stuff as well. So like I said, if you're interested in this particular model and you're interested in some of the things that we can do, go to the paper. And if you still have questions, just shoot me an email. I'm more than happy to talk about it. This is one of my favorite projects I've worked on recently. So just very quickly, for those of you who really want a very high level view of how we normally do a Bayesian analysis, step one is we start with visualizing the data. It's usually the first thing we do. We visualize the data. We might make some histograms, might make some box plots, just get a feel for what does this data look like. The next thing we're going to do is we're going to start building some models. Using the visualizations of the data, we'll start to figure out, okay, so is this data that's better modeled with a beta distribution? Maybe I should do a binomial. Is this a coin flip situation? Is this something more like a, some kind of casino game? Is this a normal distribution? Do I not know what it is? We'll start to answer those questions and start building models based off of those. Next step is we're going to validate the models against the data. And we're going to ask the question, is this a good model? Is this model capable of yielding the kind of data that we saw? And then we make inferences based on the model if it's a good model. And we will typically compare vehicle and treated models. And then, like I said before, we'll use what we call highest density interval and region of practical equivalence approach, which combines our statistical with our biological information, such as what is a biologically meaningful difference. And we'll use that to try to come to really good inferences. Believe it or not, this isn't different how we should use frequentist stats. It's the same thing. First step when you do frequentist analyses is you really should visualize the data. The next step is you're going to choose some kind of model to use. When you're doing a t-test, you've just chosen a model. If you decide you're going to do a Kruskal-Wallis, you just chose a model. You're going to do an ANOVA, you chose a model. You're going to do a regression, you chose a model. You're going to use a linear mixed model, you chose a model. All those things are subjective choices that you've made, and they come with lots of assumptions. Sometimes we call it baggage. And if you violate those assumptions, then your ability to make inferences is much more difficult. And it's the same thing in Bayesian statistics. The difference is in how we do certain steps and how we treat uncertainty. There's some philosophical differences, and we'll get into that later in the course. So do Bayesians always treat the data as normal? No. Like I mentioned, we use a variety of distributions, and here's some examples. One of the fun ones is gamma. The gamma distribution is really fun if you have data that can't go negative. We can also do truncated versions of these different distributions, and there's lots and lots and lots of ones to choose from. And why you might choose them could be for different reasons. Sometimes we'll use, I didn't mention it in this list, sometimes we'll use a Poisson model if we have counts. Sometimes we have lots of counts, in which case we could actually use a normal distribution or a gamma distribution. So the choice of model matters, and sometimes matters more than others. And we'll have different reasons as to why we will choose something. Bayesians will debate, well, you should use that or you should use this. But ultimately, for applied statisticians especially, what we really care about is the validity of the inference. So if the model is valid, then generally the inference will be valid, as well as assuming that the data that we have is good. So here's some key takeaways I really want you to remember. If you remember nothing else I said, please remember these things. Bayesian approaches let you bring historical or other similar information into your study, and that's important, especially when we don't have a lot of knowledge from our particular study. Maybe we didn't do a lot of samples, and we should have. Sometimes we can use historical information to help rectify those issues. And as the analyst, we don't always have control over the experimental design as much as we wish we had. And so we have to sometimes take the data that we're given. One of the other things that I love about Bayesian models is that we have access to a variety of distributional models. We have lots of different things to play with, to choose from. Bayesian statistics is really more about capturing the uncertainty in your parameter estimates. That's really what it's all about. We tend to use the full distribution as opposed to just the mean or the median, which is what maximum likelihood is going to tend to use. It's just the mean or the median. So maximum likelihood estimates are the basis of frequentist approaches. And using that uncertainty as part of your inference is one of the things that I feel makes Bayesian statistics very powerful. And it allows, being able to use that uncertainty, especially when we start going into risk assessment, is very powerful. And we need to start wrapping our heads around how to use that uncertainty and using data-based uncertainty factors, or data-based uncertainty, I should say, to replace uncertainty factors in the risk assessment paradigm. So that's one of the things that I'm ultimately very interested in trying to pursue with some of my research as well. Anyway, that's it for this part of the course. If you have questions, of course, shoot me an email. I hope you enjoyed the high level overview. Um, this obviously is not made to make you a Bayes expert overnight just by watching this particular set of slides. But I hope it gives you an introduction to some of what we're trying to do with Bayes and a better handle on how we can use Bayesian inference in toxicology and pharmacology. And if you're interested in learning more and how to actually apply some of these things, that's what we'll be talking about in the rest of the course. Thank you.